Hello everyone, I'm Evgeniou, and right now I will present about the individual summary paper, which has topic support vector machines. For the table of content, there is introduction, how the algorithm works, example of how the algorithm works, implementation, advantage and disadvantage, and the conclusion. So the first topic is introduction. Support vector machines, or SVM, have been recently developed in the framework of statistical learning theory by Putnam in 1980 and have been successfully applied to a number of applications, ranging from time series prediction by Fernandez to face recognition to biological data processing for medical diagnosis, and their theoretical foundations and their experimental success encourage further research on their characteristics, as well as their further use. Support vector machines, or SVM, have emerged in recent years as powerful techniques both for regression and classification. One of the central open questions is model selection. Classification is one of the most important tasks for different applications such as text categorization, tone recognition, image classification, we call array gene expression, protein structure prediction, data classification, and etc. The next one is how the algorithm works. In this section, we introduce some basic concept of SVM, different kernel function, and model selection of SVM. SVMs are set of related supervised learning methods used for classification and regression. They belong to a family of generalized linear classification. The special property of SVM is SVM simultaneously minimize the empirical classification error and maximize the geometric margin. So SVM called maximum margin classifier. SVM is based on the structural risk minimization, or SRM. SVM SVM may input factor to a higher dimensional space where a maximal separating hyperplane is constructed. The kernel selection of SVM. There are many kernel functions in SVM, so how to select a good kernel function is also a research issue. However, for general purpose, there are some popular kernel functions, which is linear kernel, polynomial kernel, RBF kernel, sigmoid kernel. Here, the gamma, R, and B are kernel parameters. In this popular kernel function, RBF is the main kernel function because of following reasons. First, the RBF kernel non-linearly maps sample into a higher dimensional space, unlike true linear kernel. The second, the RBF kernel has less hyperparameter than the polynomial kernel. And the last one is the RBF kernel has less numerical difficulties. The next one is model selection of SVM. Model selection is also an important issue in SVM. Recently, SVM are shown good performance in data classification. Its success depends on the tuning of several parameters, which affect the generalization error. We often call this parameter tuning procedure as the model selection. If you use the linear SVM, you only need to tune the cost parameter C. Unfortunately, linear SVM are often applied to linearly separable problems. Many problems are non-linearly separable. For example, satellite data and shuttle data are not linearly separable. Therefore, we often apply nonlinear kernel to solve classification problems. So we need to select the cost parameter C and kernel parameter gamma D. The next one is example of how the algorithm works. Example, the basic of super vector machine and how it works are best understood with a simple example. Let's imagine we have two x, red and blue, and our data has two vectors, x and y. We want to classify that given a pair of x, y coordinates output if it's either red or blue. We thought our are already labeled training data on a plane. The support vector machine takes this data format and output the hyperplane. within two dimensions in simply a line that best separates the text. This line is the decision boundary. Anything that falls to one side of it we will classify as blue, and anything that falls to the other as red. But what exactly is the best hyperplane for SVM is the one that maximizes the margin from both heads. In other words, the hyperplane in this case is a line whose distance to the nearest element of each state is the largest. You can see as the picture is here, and the next is implementation. The implementation of SVM is time series prediction using local SVM. An application of SVM regression was discussed in by Fernandez 1999. The problem was time series prediction. The approach taken was the use of SVM regression to model the dynamic of the time series and subsequently predict future value of the series using the constructed model, instead of using the standard SVM regression formulation described before. A variation developed in Sollich in 1998 was used. Using this variation, the ellipse parameter of the SVM regression loss function is automatically estimated. Furthermore, Fernandez 99 used an approach to learning which is different from the standard one. Instead of developing one global regression model from all the available training data, Fernandez developed a number of SVM regression models, each one training using only part of the initial training data. The idea, which has been suggested in Botto and Papnik in 1992, is to split the initial training data set into parts, each part consisting only of training data that are close to each other in a Euclidean distance sense. Then a local SVM is trained for each subset of the data. The next is advantage and disadvantage. The advantage: SVM generalizes the new sample very well only if C and R parameters are wisely chosen in Gaussian kernel. This also meaning that selecting a suitable value can guarantee a well performance even when the input has some bias. In this method, not supposition about the practical form of transformation to make data linearly separable is necessary. This is due to the fact that the kernel holds a non-linear transformation. Since this transformation happens on a strong theoretical background, no further human expertise is needed. When the optimally is rounded, SVM can produce a unique solution. This forms a fundamental difference of SVM and neural networks, which produce multiple solutions based on local minima, which make them not trustable over different samples. And thus, is selecting a suitable kernel would end up stressing on similarity between similar companies simply because the more similar two companies are, kernel value would be higher. Hence, at the time of new company's classification, the financial ratio value would be compared to support factor 1. At the end, the new company would be classified in the group which has the most similarity to. And the disadvantage is SVM have also some disadvantage. A common one is the lack of transparency in result. Since the dimension might be very high, SVM might not be able to show the company score as a parametric function based on financial ratio nor any other functional form. Financial ratio rate is not constant, so its financial ratio marginal contribution is variable. By utilizing a Gaussian kernel, each company has a unique weight, which is based on the difference between its own financial ratio and the one of support factor of the existing data sample. And the last one is the conclusion. SVM are trained by solving a constraint quadratic optimization problem. Among others, this implies that is a unique optimal solution for each choice of the SVM parameters. This is unlike other learning machines, such as standard neural network trained using backpropagation. There are a number of directions for possible future work. SVM has been successfully used for medical diagnosis by Farrell Plus in 1999, methods for dealing with unbalanced training data or for biasing the performance of an SVM towards one of the classes during classification were suggested and used in Farrell Plus in 1999. By using all 6,817 gene expression measurements, an SVM can achieve near perfect classification accuracy on the ALL or AML dataset. Furthermore, an even larger dataset has been used to demonstrate that SVMs also perform better than a variety of alternative methods for cancer classification from microarray expression profile. SVM analysis can be applied to a wide variety of biological data. As we have seen, the SVM boasts a strong theoretical underpinning, coupled with remarkable empirical results across a growing spectrum of applications. Thus, SVM will probably continue to yield valuable insight into the growing quantity and variety of molecular biological data. And that's all from me. Thank you for your attention. Let's meet in the next topic.